Okay, folks, hopefully you can hear me and see me and everything's working okay. I'm Mark. Welcome to Dublin Maker. Yeah, that's okay. Sorry. Um, right. It's our first time live streaming, so you have to bear with us. Right, I'm Mark, and with me over here, behind the camera, behind the screen, is Niamh, who's going to be helping us run the stream. And shout hello, Niamh.
Hi.
You probably just about hear that. Okay, so we are JellyLab. We're a group of researchers based in the School of Medicine in UCD, and we got a few different things to show you today. So we're going to show you some ways to make sort of laser art with some homemade optics. We're going to show you that in a little bit. And we're also going to show you some real anatomy with the sort of thing you can pick up from the butchers. And Tom Flanagan will be joining us later to do that. And then after that, we've got, we're going to be talking a little bit about some of the work we do in exploring the sea and how we do that. And we're going to finish up with one of the with an experiment on one of the little tiny comb jellies, the little marine animals that we work with, which you can maybe just about see those little round things over there in the corner. That's our aquaria, where our jellies live. Hence JellyLab. And we're going to talk to you a little bit about that. But first, what we're going to do is we're going to talk a little bit about microscopy. Now, we love microscopy around here. We build microscopes ourselves all the time. And some of the microscopes we build are a little bit fancy. Some of them are pretty basic and pretty simple. The most recent one we've made is one which essentially was built out of a 3D printer. We took a 3D printer apart, rebuilt it as a microscope. Brilliant work, and it was George Merces is the guy who did that. And when you build your own microscopes, when you build your own optics, there are suppliers, there's people you can go to who will sell you the different pieces and parts, and they all kind of go together, and they literally sort of screw together like this. And you've got your little lens elements and tubes and things like that. And people often refer to it as optical Lego because of how it all just sort of slots together and fits together. And that's a good analogy. It is quite like Lego. But you know what's more like Lego? Lego. So we've been thinking about, can we actually make a microscope out of Lego? And can we make a microscope as much as possible out of Lego? And that's kind of what I'm gonna start today by talking you through some of the work we've done on that. Now, so what we have here is some bits and pieces. I'm going to take you through a little Lego microscope that I designed. I'm not going to give you detailed instructions on how to build it because this is ugly and horrible. Okay, the whole principle behind this design was to try and make something as simple as possible. There are lots of really fancy Lego parts and components and gears and motors and all this sort of stuff. We didn't actually want to use any of that. We wanted to use the simplest basic Lego pieces we could kind of get our hands on. So that's what we're going to be really focusing on. And the idea is that if you understand the basic principles of how to build a microscope, then actually, and you've got a pile of Lego on hand, you can probably make your own. There's a couple of little things that little extras you're going to need, but I'll take you through those in a moment. The important thing to know is that building a microscope is actually really easy. It's probably a lot easier than you think. So most people kind of think about, when they think about a microscope, you have a picture in your head of what that looks like. But a lot of the parts of that microscope are actually really simple, and a lot of the structure that you see is kind of holding it up and making it steady and stable and all that sort of stuff. It also gets a lot simpler when you don't have to look into it. So a much easier way, so one way to see things down a microscope is to look through an eyepiece. Eyepieces are actually a bit fiddly to use. And it's much easier actually to use a camera. So if you have some sort of camera and you use that instead of the eyepiece, then I think that's actually an easier device to use. So we're going to be doing that. We're going to be doing some digital microscopy. And we're going to be doing it cheap. Right? So we're going to use a Raspberry Pi, which I've got one here. There. I'm going to be using that in a bit. Sorry, it's all wired up, so you can see that there. And we're going to be using a Raspberry Pi camera. Okay, so this is the newer type of Raspberry Pi camera. I think they call it the HQ camera. And importantly, the difference between that and the original Raspberry Pi camera is it's got a bigger sensor, but the really important thing is the screw mount on it. So it contains what's called a C-mount thread, and that's just a standard way of actually attaching a lens. So here we have the camera here we have a standard C-mount lens, and this is just really basic sort of thing, and it just screws in like that. Very, very simple. The thing is, C-mount is a standard for, C actually stands for Cine. It's an old standard for cinema cameras. It's often used now on things like security cameras and things like that, but it's also used on a lot of microscopes. So it's perfect for our purposes. So that's the one thing that we're going to need. We're going to need some sort of sensor. And actually using a camera means we get rid of all of that mess of eyepieces and all of that sort of stuff. And it's going to make our life a lot easier. Well, the other thing that we're going to need is some sort of lens. We're going to need some sort of objective lens. And we got some different objective lenses here. Now, that's actually all you need. So if you have a camera and you have a lens and the lens is pointed at the camera, then you've basically got a microscope. You've got all of the components. All you need to do is plug them all together, is hold it rigid and aligned and straight, and you've basically got a microscope. It's a little more complicated than that, but that's basically it. So because of that, Lego's actually ideal, because Lego is pretty solid. It's pretty easy to get it straight, and it's pretty rigid, and also it's not transparent, and that makes life a lot easier. So that's our basic sort of principle. Okay, so the first thing I'm going to talk to you, so the problem that we have here is we've got Lego, right, which connects together because it's all blocks and studs, and Lego is designed to connect to Lego. And then we have these optical components, and I talked about this C-mount, this threaded part here. And then if we look at this microscope lens down here, there's a little threaded piece down at the end. So how do we connect that to Lego? And that's been our challenge from the start. So we cheated, and we made our own Lego bricks. So this is one of the ones that I made. So I'll show you this. So this is a 8x10 stud Lego brick, standard size Lego brick, and it's got a hole in the middle, and that hole actually has threads in it, and those threads are a special type of thread called an RMS thread. RMS is the most commonly used thread on microscope objectives. So that means that I can take this and I can thread it in here, and oh, I'm threading it in the wrong side. Okay, I can take this and I can thread it in here, and now I have a Lego brick with a microscope lens sticking out of it. So where did this Lego brick come from? Well, we made it ourselves. We designed it ourselves and 3D printed it. You can find the STL file for this on Thingiverse, and so we've also put it on the NIH 3D Print Exchange. So if you've got access to a 3D printer, you can grab one of these. You can grab the file and download it and print it yourself. That's the RMS thread. At the other end, we need to connect the C-mount, the camera, and we basically did the exact same thing. Here's one, and I've just connected a little C-mount extender on that. There's also a couple of extra bricks. So it's Lego, it works. You can still attach other Lego to it, even though it's 3D printed. You need a good, well-tuned 3D printer to get the tolerances just right. But the bottom line is it works. So we then take our camera and we can thread it on like this. And now we have a camera mounted on a block of Lego. And after that, everything gets a lot easier. Now, I just want to make a little point about microscope lenses, because you can find the Raspberry Pi, you can find C-mount cameras. There are lots of other C-mount. You can get just standard USB C-mount cameras. You can get them pretty cheap. That bit's easy. The objective lenses, microscope lenses, can be a bit tricky to find. There's lots and lots of different types of microscope lenses, and you can pay anything from 20 euros to probably about 20,000 euros on a single microscope objective. So as you might imagine, they're not all created equally. But for our purposes, the cheap objectives are actually the best, and they're the easiest ones to use. So we're not trying to do anything fancy here. We're just trying to build a simple microscope. So we just need simple objectives. Now they come in lots of different sizes and lots of different connectors, but the most common ones on the cheap ones are RMS threaded. So that makes our life easier. So if we just find random cheap microscope objectives, the chances are that they are RMS threaded. The other difference between different types of objectives, different types of microscope lenses, is the magnification. So this one here is a by 10 lens, and the one which I stuck on over here is actually a by 4 lens, a much lower magnification. Low magnification is going to be a bit better for what, a bit easier to use for what we're trying to do. But what do those numbers actually mean? And there's another number that you'll find on an objective, which is actually really important. So written underneath this, so it says by 10, and then there's a number after that, which is the numerical aperture. Don't worry about that. We don't need to worry about that right now. And underneath it says 160, or is it 180? I don't have my glasses on. It's either 160 or 180, which is just written under the magnification. And what that is the length. This is what's called a finite conjugate lens, right? And that just means it's designed to just point straight at a sensor or an eyepiece. There's nothing goes in between it. This objective is designed that the light comes out the back of it. So the front end of it points at whatever it is you want to look at. The light comes out of the back and focuses 160 millimeters away. So if we have a sensor at 160 millimeters away, then we'll get by 10 magnification. So each lens will have that written on it. Some of them, though, don't have that number. They don't. Some of them might have 160, some have 170, some have 180, but some of them have a little infinity symbol. They're slightly different, and they tend to be the more fancy lenses. They're called infinite conjugate lenses, and the problem with infinite conjugate lenses is the light coming out of the back of them focuses on infinity. It never focuses. So you need an extra lens in there to point it, to focus it onto your sensor or onto your eyepiece. There are advantages to using them, which I'm not going to go into, because unless you're a microscopy nerd, you probably find that boring. The one thing I will tell you is just avoid those, right? So if you're going to try to do something like this, just get yourself. But almost every cheap lens is finite conjugate. It's be 160, 170, 180. And it doesn't matter which number it is, because we're not going to use it as intended. I'm going to explain how we're going to use that in a minute. Now, right, so let's get started. I'm going to take you through some of the basic components. So some of this is partially already assembled, as I put before I got here, so just to save time, because I'm sure you don't want to just sit here watching me assemble Lego bricks. And this is just a little base, and all I've done on this is just put some flat plates down the middle, and that's going to give us a nice smooth surface down the middle. And that's going to become important when we are actually focusing with the focusing mechanism, which I'm going to explain in a little bit. Right, that's that. Then we actually have some supports at the side, which I'll come on to in a second. But let's actually build, let's put our camera and our lens together. Let's build the actual microscope part. So we've already connected our camera onto the piece of Lego. So now all we're going to do is connect that onto this block here. So I'm just going to... It's a little tighter than a standard Lego brick, because it turns out that my spare room is not quite the same level of manufacturing accuracy as the factories they build Lego in, but it's close enough. Right, so now we've got a camera at one end. So if you look in there, I'll lift this up. There you go, you should be able to see the camera in there. You'll notice it's off center, and the reason for it's off center, I don't remember. I designed it like that, and there was probably a reason, but I don't remember what it was. But that's the design we have to work with. It doesn't seem to make a difference, because as long as everything's aligned to each other, then it's all fine. Right, then we're going to get this piece, which is our objective lens. And we're going to start with just the by 4, because it's going to be a little easier to work with. And we just pop that on there. So again, it'll just pop into place, because it's all Lego. And now we have, essentially, a microscope. So we've got our objective at one end, and we've got a camera at the other, and the light that comes in the objective is going to get focused on the camera. So remember I mentioned about this 160 millimeter length? That is not 160 millimeters. But this is the important thing about this is how we're really abusing the optics on this. The important thing to remember about how lenses work, okay? So if you're looking at me, so you're looking at the camera, I'm pointed at a camera right now, and that camera should be approximately, if I've set it up correctly, it should be focused on my face, right? Stuff in the background is probably a little bit out of focus, and if I move my hand all the way up, then it gets all blurry and out of focus. Right, now, so that means that, and that's exactly what's happening and notice as well, as my hand gets closer, it gets bigger, okay? So magnification, when we magnify things with a microscope, all we're doing is we're focusing on things that are really, really close up, right? So if we could focus in on my hand, right now it would look really magnified, and you would see my fingerprint. You can't really see it because it's out of focus. So that light is focusing somewhere else, right? It's not focusing on the camera, it's focusing on the sensor in the webcam that I'm talking to right now. It's focusing somewhere slightly different. So all we need to do is actually change where it's focusing. Change that distance. And this means that if we take something like this, and instead of having 160 millimeters, we have something much, much shorter, then instead of focusing on something really, really close, it's focusing on something a little bit further away. So it's not going to be as magnified. So we can actually adjust the magnification of our lens by changing how many layers of Lego bricks we have here. In this case, I've got 1, 2, 3, 4, 5, 6 Lego bricks between the top and the bottom. If I added 4, we would have less magnification. If I added 8, we would have more magnification. I can keep going to extremes in either direction. The problem is, because this is designed for 160 millimeters, the optical quality will be a bit rough. But to be fair, we're building a microscope out of Lego. We're not really too concerned with getting the absolute top precision engineered quality out of this microscope. But you might be surprised at how good this actually works. So now the thing is, we've got to get this, and we've got to actually be able to control it and point it at our sample. And that's where these little support things come in for. So I'm going to pop these here. I hope my mum was watching, and she's very proud because her son is building Lego on the internet. You know, dreams do come true. Right. Okay, I'm going to do one more thing. I'm going to point it out here, and it's just on the at this point here. I've got this little kind of slopey, rampy piece, and I'm just going to pop that in there for a moment. Okay. Now you'll see why that's there in a second. Okay, now I'm going to take the entire assembly. I'm just going to move this over a bit, and you see you've got little sticky out bits on the side. They are 4 studs apart from each other, which is exactly the same height, the same distance as those pillars. So I'm going to just slide this down here. Now, what that's going to do, and I'm just going to add some extra little pieces, just to kind of trap that in there. But what this is going to do is it's going to give us a bit of support and restrict. Whoops. I got it. I think I got it. I don't got it. Oh, I do got it. Got it. Right. That's going to give us a bit of support and restrict the movement of this, the actual microscope. So now it can't move forwards and backwards, and it can't move left and right. So the only way it can move is up and down. So this is going to basically form the basis of our focus mechanism. So we need to make sure that whatever it is we're pointing this microscope at, that we can actually bring it into focus. Okay. There we go. And now we've got movement up and down. It's a little bit clunky still, but we'll get there. There's our objective lens. Camera's below. And now we're going to put something on top to hold our stage. And this is just a piece of Lego I just made with a hole in the middle. I just threw some pieces together, made a gap. Okay? So, I'm going to line that up. It's already looking ridiculous. That's not quite right. No. It's falling apart. Right. Now we got movement up and down. And now we can put our sample on this. So, the problem is we need to be able to control the movement. So how do we do that? Let me move everything down here a little bit. Okay. Now, that's where this bit comes in. Now, when I was trying to think about how to build a Lego microscope, this was the bit that got me kind of most confused. I was trying to work out how do we build a focusing mechanism? How do we allow something to go up and down? And I came up with all sorts of complex solutions to this. And then a few weeks ago, I was actually taking apart a big microscope, salvaging it for parts. And I discovered that the focus mechanism of it basically involved the entire sort of lens assembly sat on top, and there was a little ramp. And there was a motor that just pushed the ramp, and as it pushed the ramp forward, it pushed everything up and down. And I thought, well, that looks very fancy and expensive, but I bet you could make it with Lego. So that's why we have these smooth pieces on the bottom here. So if I take this here, and remember I put in that little kind of ramp bit, so we're going to push this underneath, and that now will give us our focus. As I slide this backwards and forwards, the entire assembly moves up and down. So that's our focus. Right. Now, let's just see if we can get this camera started. And I'm just going to get the Raspberry Pi up and running. Just bear with me a second. Okay. Aha. Right. Okay. So, the last thing we need to do is we need to be able to put some light in. And I had a great idea for this, but I'm going to show you why it doesn't work. So I built this little, I had a little extra one of our little custom-made 3D printed Lego pieces left over. And I also had a torch, and it fits perfectly into that space. So I had this brilliant idea that what I would do, we put our little microscope slide down there, and I had this brilliant idea that what I would do is I would pop this on top. I'd get my torch, turn it on, and sit it right in there. And I thought this is going to be great, but it doesn't work. I'll explain why in a second. Let's take that off. I'm just going to cut now to a slightly different view. So, what you're looking at here is the feed from the Raspberry Pi camera. We get a little bit of light there, and that doesn't look too bad. And we put that in. Aha! You see that flickering? So that's a problem. And the reason for that is because the LEDs in this are switched on and off. And that's how it modulates the frequency, modulates the intensity of the light. And that flickering is just overlapping with the shutter on the camera, and that's just creating problems for us. So it's a lovely idea, but it doesn't work. Okay, plan B. And I only discovered that just before we went live here. So I'm going to take this off. It looks great. It doesn't work. I'm going to go with something else. I'm going to move this over a bit closer. And it turns out we got a little ring light here. And if I take this, so you don't need fancy lighting for this. I'm just going to take this, I'm going to angle it down. I'm going to put it over my sample. Now, If I line that up there, so you should be able to see we got a hint of something. There's something there, but it's not quite right. Now, let's see if we can adjust this and bring it into focus. There we go. A bit of a shove there. I will admit the focusing mechanism is not the most precise. It sort of works though. So, this is just a piece of tissue sample, and you can see there we've got microscopic images. Right, let's try something else. I've got another one over here. I'm not sure how well this is going to work. And this is a little... Let's see if I can find it. There we go. Oh, look at that. This is a small little marine invertebrate that we caught when we were down in Howth Harbour, I believe this came from. Came up in one of our nets. And you can see there beautifully the detail in the legs and the face, the structure, the head. There we go. And it's a microscope built out of Lego. Right. Excellent. Let's go back to here. Okay. So, that's one of the things that we can do. Let me just get that out of the way. Move that back here. There. Make me look prettier. Now, so this is one of the things that we do. We can build optics, we can build microscopes. But there's lots of different things you can make yourself just by playing with optics and things like this. So what we're going to do now is we're going to show you some of the other optical work that we do, and we're going to show you how to basically create some pretty laser art using some homemade optics. And this is some work that myself and Niamh did just during the week. Say hello again, Niamh.
Hi.
That was Niamh. Okay, here we go. Okay, so you can tinker around with optics and maybe make yourself a microscope or something like that. But if you're happy to kind of play around with little bits and pieces of optics and light and things like that, there's a few other things that you can do too. And we're going to show you one of those now. We're going to show you something kind of fun and interesting that you can do with lasers and how to make your own optics to do this. Now, the sort of lasers that you find in a research lab like this usually are quite expensive, they're quite specialized, and you know, it's not the sort of thing most people are just going to pick up to tinker around with. But you can get really good lasers, something like this, which is the type that we use a lot of, for about 30-40 euros. Now, these tend to crop up quite a bit on eBay. What they look like is you've got this little sort of aluminium black box, and this black box is actually a heatsink. Technically, these aren't lasers. What these are essentially LEDs. They're the same as an LED. And you've got some little lenses in the front which will focus that light into a single beam. So rather than kind of spreading out like you'd normally get with an LED, you get a single focus beam, which is essentially what a laser is. It's just a whole load of light all pointed in the same direction. Now these sort of things you can pick up cheap because I think, and I'm not 100% certain, but I think these are actually recycled from things like the sort of laser light shows you tend to find in cheesy nightclubs and places like that. So when you pick up one of these, you'll tend to find that they ship with a wired connector on the end, and they'll typically ship with one of these, which is a little PCB, a little circuit board, which actually gives you the control of the laser. Now these are really important because most of these lasers require a little bit of circuitry to actually sort of control them. But these things are very, very simple. So essentially the laser will plug in here into the board, like that. And then there's usually, you just need to connect power to it as well. So there's usually a power connector somewhere as well. These don't typically come with manuals, so it can take a bit of playing around to work out which is the laser connector and which is the power connector and so on. And they're quite tolerant of what power supply they'll take. We've hooked up a little barrel connector here. Between 9 and 12 volts works really well, so you can actually make these, connect them to a 9 volt battery, and that tends to work quite nicely. So if you're going to be tinkering with a laser, the most important thing you need to think about is how to do it safely. So the first bit of advice is whatever laser you get, try and get yourself some laser safety glasses. So laser safety glasses will block out the specific color of light, the wavelength of light that a laser will emit. this will allow you to play with your laser much more safely. So it's a really important thing to do. So the other thing that's important to bear in mind if you're playing with one of these laser diodes is that not all laser diodes are created equally. And the most important characteristic of any of these is the class of laser that it has. So the lasers are classified by different classes from 1, 2, 3, 4 based on really how much energy they kick out the end. And the more energy that the laser kicks out, then the more potentially dangerous it is. Class 1 lasers are the safest. Class 2 lasers are pretty safe as well, but you don't want to stare directly into the beam. Class 3, which is what we're using here, you definitely want to avoid direct exposure of the beam to your eyes. Class 4, most dangerous, generally speaking, don't touch them. There's potential for serious injury, so Class 4 lasers, not really suitable to be playing with. But even a Class 3 laser, you need to be very, very careful. So always err on the side of caution. And even if you're not looking directly at the beam, always remember that you may be looking at light reflected off the beam into your eye. So if you're playing with a laser, think about reflective surfaces around you. So if there's anything shiny and reflective, like my head, then make sure you're not pointing the laser at that as well. The last characteristic of the laser, which is important as a general rule to bear in mind, is that each laser has a specific color, a specific wavelength. And this actually corresponds to the amount of energy that it kicks out. So at the safest end of the spectrum, all other things being equal, are the red lasers. Red wavelengths of light have the lowest amount of energy. Beyond the red wavelengths, we get into infrared, and that has even less energy. But we can't see it, so not really that much fun to play with. Next we come to the green lasers, which are generally speaking more dangerous than the red lasers. And next we come to the blue lasers, and blue lasers have the shortest wavelength, and they have therefore the most energy and are potentially the most dangerous. So if in doubt, avoid blue lasers. Okay, we're almost done with the little safety warning. There's one very last very important thing I need to point out. What we're going to be doing here, what I'm going to be showing you here, involves basically shining a laser through a lens. Now, a laser is essentially a parallel beam of light. But if we take that and stick a lens in front of it, then we can focus it onto a single spot. And when you take that energy and focus it into an even tighter area, then it gets even more dangerous. So as soon as you stick a lens in front of a laser, always be aware that you're potentially increasing the risk of what you're doing. And even with simple little lasers like this, which are relatively harmless, you take this, you put a lens in front of it, and you focus it onto something, that's a great way to start a fire. Just to be clear, I'm not recommending you do that. It's just that's a thing that's possible to do. Okay, so that's the safety bit out of the way. So now let's have a little bit of fun with lasers. What we're going to do is we're going to be taking a laser and sticking a lens in front of it. And what that lens is going to do is change the path of the light. So essentially all a lens is a curved surface which has a different refractive index. And what that basically means is as light goes through it, it's going to change direction. And that's essentially all a lens is. It's a way of changing the direction of light. So now we have light coming into the lens, and then that's going to, in a straight line, in a parallel beam, we're going to pass it into the lens, and then we're going to change its direction. Now, this is essentially how all lenses work. So the camera that's recording me right now has a lens in front of it, and that's taking the light from me and bending it and changing its direction onto a sensor in that camera. Okay, so let's just take a little example. This is a completely normal convex lens that most people will be kind of familiar with, presumably the sort of thing you might have in your glasses or something like that. It's just a slightly smaller one in a little ring here. And as I pass this closer, you should see my head flipped upside down. It's all a bit blurry and weird. There we go. Okay, why is it doing that? Because it's changing the direction of the light. It's changing the path of the light. Oh, look, there's my head upside down. That's weird. Okay, right, so that's a lens. So that lens that we were looking through is essentially a type of spherical lens. And what that means is it's like you've got a sphere of glass and you just cut a slice through it. And this is just what one of those looks like from the side. Okay, and as you can see, as we turn it around, I'm turning it around in my hand, and it's curved in every direction. So what happens is, as light enters this, it's going to change direction in every direction. But not all lenses are like that. There's another type of lens, which is called a cylindrical lens. And cylindrical lenses are only curved in one direction. So here's a cylindrical lens, and as you look at that there, that looks kind of straight. But if we look at it on the edge, you can see it's curved. So it's essentially just a cylinder. Now, what effect does a cylindrical lens have? So if we take something that doesn't have a curve, we shine light through it, it's just going to go in and come straight out the same way. Right? Just like that's how your windows work. Right? Light comes straight through and doesn't really change direction very much. It's the curvature of the lens that gives it its effect. So in this case, a cylindrical lens is curved in one direction. Now I'm going to move this closer to the camera, and you'll see it's distorting my head, making it sort of skinnier, and then it's going to get weird and fatter in one direction only. This is not a very good lens. I'll explain why in a moment. Right, so it's bending light in one direction but not in the other. So what happens when we pass lasers through this? So let's take a laser and shine it through a spherical lens. And remember, it goes in traveling in a straight line. And as it comes out, the light changes direction and now it's spreading out. So it creates this cone of light. So it's spreading out in every direction. Direction. But what happens if we take that light and pass it through a cylindrical lens? It's only going to spread the light in one plane. It's only going to spread the light where it's curved, and it's not going to spread the light in the other direction. So here we have two different lasers, and both of them have cylindrical lenses in front of them. One is oriented horizontally and one is oriented vertically. And what you can see here is that it's creating a sheet of light. So you can imagine this almost like a triangle of light extending out from the lens. And this sort of light sheet creates a really interesting effect because it creates essentially like a wall of light. And that's what we've got here. Okay, so in a moment I'm going to show you some interesting things you can do with these light sheets. But first I'm going to show you how we make them. So I've already told you how you can get lasers quite cheaply. But the problem is that the cylindrical lenses, if you go to an optical supplier, as a specialist place that sells specialist lenses, they're not exactly cheap. But for the purposes of what we want to do, if you want to just get the sort of effect we're going to show you in a moment, you can actually make your own pretty easily. So the first thing that you're going to need for this is something that is tube shaped. Now, we just happen to have lots of sort of test tubey type things lying around the lab, so we're just going to use two of those. One of them is bigger than the other, doesn't really matter. And we're going to use those to create a mold. And we're going to make that mold from silicone. So we take some silicone, mix it up, and it's liquid at this point, and then we put the two tubes into the silicone. And when the tubes go into the silicone, we then let it set and let it cure around it. And this takes about 24 hours. So once that silicone has set, all we need to do is peel it away from the tubes that we used, and we're left with a nice flexible mold. Now we had a bit of a weird occurrence with this. So one of the tubes that we used actually used to have print on it. But when we put it into the silicone and took the tube out, it left the print behind. You'll see what happened next in a moment. So the next step in the process is you want to get yourself some nice clear acrylic. The acrylic that we use comes in two parts or two liquids that you mix together. And you mix these two components together and then pour it into the mold. The thing about acrylic, when you mix the two pieces together, you'll often end up with bubbles within it. And these bubbles can scatter the light and cause you a bit of a problem later on. So to get it nice and clear, one trick that you can use is to just give it a quick blast with a heat gun. If you don't have a heat gun, a hairdryer on high will probably do basically the same thing. So just to note, I just happen to have a little hemispherical mold, silicone mold. So I had some acrylic left over after I'd filled everything else, so I also filled that too. When the acrylic is set, again that takes about 24 hours, then you can just pop it out of the mold. This is what the hemispherical one looks like. That's actually that lens that I was showing you earlier, which we just made ourselves out of acrylic. Just pops into this mold like that, pops out of the mold like that. We then popped out our cylindrical lenses, and you may remember I mentioned we left the print behind on the mold. Well, when we took the lens out of the mold, it took the print with it. So we now have this lens that has lines and gradations written on it, which isn't really that useful, but I guess not a disaster because we have another one as well. Right, so here is our nice little cylindrical lens, and again that's the one that I just showed you earlier. All we need to do then is just stick it on the front of our laser. So we got our little diode here, and all we do is just stick it on with a little bit of tape. Like that. And like that. Okay, so now we just have the laser with the lens just taped on the front. So with this attached, now, so the curved part it's curved in this direction here, but not in this direction. In that direction, it's basically just straight. So as the laser comes out of here, goes through the lens, in this plane, it's not going to move. And in this plane, it's going to spread out and create a light sheet. And this is what we're going to use in our little demonstration. So as you can see, it's pretty easy to make your own lenses if you want to. But if you really don't want to, you can get basically the same effect from things that you probably have lying around. One of the things that actually works really well for this is something like the stem of a wine glass. Or basically anything that is cylindrical, that is rounded, and is refractive. So that means it's made of glass or something else transparent, possibly containing water or anything like that. So even something like this great big bottle here essentially works as a cylindrical lens. Does basically the same thing. So the last ingredient that we're going to need is essentially something to shine that light sheet into. And for our purposes, we made this little Perspex box. But really anything will do for this. So we just got some pieces of Perspex, 5 little squares of this, and stuck them together with silicone, and gives us this nice little, like a mini aquarium. So we've got our little chamber here. We filled it with water, and we set up our laser over here, so it's shining the light sheet through it, and that's arranged vertically like this. And then the last thing we do is we just pop a piece of black card behind us, and this is going to stop any of that stray light bouncing around and potentially getting in our eyes. So again, just a little safety addition to the process. Then we take our camera and we point it at the side of the tank, so it's looking onto the light sheet.
everybody. This is a new face for the JellyLab. So my name's Tom Flanagan. I'm a member of a different lab here in UCD, but I work closely with Mark, who runs the JellyLab. And Mark, you know, as the name suggests, with his lab, he focuses on jellyfish and other invertebrates, but he has an interest in the heart and the cardiovascular system. But jellyfish don't have hearts, so he asked me to kind of step in and show you a little bit about hearts, which is my main research area. Before I do anything, I just need to say hello to two very special little boys, Jack Flanagan and Leo Flanagan, who are watching from Blessington in County Wicklow. My little guys, so hi Jack and Leo. So today, as you can see in the bench behind me, we're going to talk about hearts, the structure of the heart, and we're going to do a little bit of we're calling it a garage dissection of the heart. So we have several hearts here from the butchers. So all these little small ones that you can see here, these are from lambs, and then we have this massive one behind those from a cow. Okay, and I suppose we set up this particular session because we thought it's something that people can do at home, whether they stream this afterwards, do it basically a DIY dissection of the heart. Anyone can access hearts at the butchers, and I suppose this stemmed from the remote learning we've had to do at the university this year. So myself and Mark both teach in the anatomy department in the School of Medicine here, and we had to come up with ways to be able to dissect tissues and organs remotely. So a few months back we organized a Zoom dissection of the heart. So everyone in our medicine class basically got their own hearts, whether they were based in Ireland or based in the UK or based in North America. Most people were at home for the duration of the year. They put their hearts in the freezer, and then they called in at a scheduled dissection, and I led them through the dissection, and it was a great success. So if we flick over to, where's my mouse gone? Okay, my mouse has just magically appeared here in front of us again. I'm going to just go over to the, there we go, to camera mix and transition, and okay, here we go. So what we have in front of us here is a lamb heart. Okay, now most people know the main function of the heart. It's to pump blood around the body. Okay, but in reality it's two pumps. So there's a pump on each side of the heart that's separated by a wall. Okay, and we're going to be dissecting through that and having a look at it. The heart looks nothing really like, you know, your conventional love heart. Okay, apart from the fact that it has a pointy bit at the end. Okay, the apex, and up at the top you have lots of structures that essentially look like tubes. Okay, and that's important because each side of the heart, each pump in the heart, has an input and an output. So they have vessels passing in to each chamber and vessels passing out. And we're going to talk in a moment about why there's two separate pumps. Okay, now I'll just pop this up here as well. We said it was going to be basically a garage dissection, so I'll pop back out here to webcam. I'm just looking for an excuse really to change the camera views. So normally this is what we'd have in the dissection room. Okay, so this is a dissection kit with lots of different tools, okay, surgical tools, but we want you to be able to do this at home yourself. So we've kind of taken various stuff from the garage that you can use instead. Okay, so instead of a scalpel, you can use a steak knife. Okay, this is meat. Okay, this is meat that we're working with here. So a steak knife is perfect for this. Most people wouldn't have a forceps at home, but you probably have pliers out in the shed. Okay, and then we have, okay, not in every toolbox, but these little punches, okay, are good for probing. Okay, so this is our heart. Okay, now the obvious thing you can see on the front here, oops, which view am I on there? On this one. Okay. So we're not seeing the, oh yeah, that's, yeah, delay in that. Cool, ignore that one. Okay, so this is our heart here. Now, the first thing you can see really is all this white material. That's fat. Okay, and I'll get a nice lean heart here to put side by side. So here's a nice lean heart on the left. Okay, very little fat here. But the fat is quite normal, okay, on hearts like this. And it generally tends to form around the blood vessels of the heart. So here we have just that line there is one of the major arteries supplying the tissue of the heart. And I suppose the interesting thing about the arteries supplying the heart is they're around the edge. Okay, and the main reason that they're around the edge of the heart or on the outside of the heart is, if you can imagine, the heart is contracting and relaxing all the time. If all these vessels, the major vessels, were inside the wall or inside the main tissue, the blood is going to be blocked, okay, passing through the vessels. But there's two examples side by side of a kind of a fatty heart and a very lean heart. Now, I mentioned a few vessels. Okay, so this structure here, instead of considering this as one heart, let's think of it as two hearts. So as you look at that, that's the position the heart would be in the chest. Okay, if I was looking at a patient, in this case this lamb, okay, the heart is going to be positioned here with the apex or the pointy bit pointing down to the left hand side, okay, as you look at them, and this bit up here is the right side of the heart. And this line down here is a good marker for the wall separating the two pumps. Okay, over here, the right side of the heart, this is mainly around to the front of the chest, because as the heart develops in the mother's belly, it twists, okay, during development. So this is the right side of the heart, left side of the heart, and the rest of the left goes around the back. Okay, the right side of the heart, its main function is to receive all the blood from the body. So its input is from veins that carry all the blood from the head and neck, the arms, the legs, the thorax, abdomen. Okay, all that blood comes back to the heart into the right side. And that pumps that blood out to the lungs. Okay, so when blood comes back to the heart, it's depleted of oxygen. That's the reason that blood has to be sent out to the lungs. So that's the purpose of the right side of the heart. It's a pump out to the lungs. Okay, in the lungs, which are right beside the heart, anyone who's not familiar with thoracic anatomy, the lungs sit either side of the heart, and gas exchange takes place at the lungs, okay, into the blood. And the oxygenated blood, as we call it, returns back to the left side of the heart, okay, over this side. So that has vessels coming into it, okay, pulmonary veins, and that left side pumps all the blood out to the body. Okay, so that's why the heart has two pumps separated by a septum or a wall down the middle. Right side receives blood, sends it to the lungs. Left side receives oxygenated blood from the lungs and pumps it out to the body. And we're going to see how the structure of the heart is adapted to these functions. Now, one thing I didn't mention is the heartbeat. Okay, so we're all aware of the heartbeat. It contracts and relaxes, contracts and relaxes, contracts and relaxes. And because of that, because it's not like, you know, a constant flow, okay, if you think of your kitchen sink, you turn on the tap, there's a constant flow of water out. But it's slightly different in the heart. So there's a squeeze that pushes blood forward, but as the heart relaxes, the blood is going to move backwards. Okay, and we don't want blood moving backwards. We need a constant forward flow of blood. So that's why we have heart valves inside the chambers. So we're going to do a bit of cutting, okay, to see some of these structures. And I'm going to start over here with the right side of the heart. Okay, if we just turn this up this side. Any heart that you get from a butcher will have some tissue missing. Okay, so here's a good example. You can see a hole in one of the heart chambers here already. Okay, that's just the way it comes from the butchers. But this hole is into that first chamber coming back from the body, which is the right atrium. So blood pours in through veins to this right atrium. Okay, and its next target is into the right ventricle. So I just pop my finger down there. That's going into the right ventricle. Okay, so you should be able to see my fingertips, just the bottom there. And the wall of that right ventricle is quite thin actually. I mean, this is all muscle. Apart from the fat we see, the rest of this is all muscle. And this is quite thin. So the first thing we're going to do is cut into that right ventricle just to have a look. So again, if anyone is following this recording, just be careful if you're using a knife like this. Okay, please get supervision if you're not an adult. So what I'm going to do is just cut just beside this vessel here. So this is where our main chambers, the ventricles, are separated. So if we just cut down along there with our steak knife, we're just going to create a little window. Okay, so that's the first thing you can see there, is how thin that wall of the heart is. Okay, that's the right side of the heart, and we're going to see how that's very different to the left side in a moment. Now we'll just cut across this way. Okay, so now there's a few really nice structures that we can see in here. So let me just pop that back so you can see the window we've created. So we're opening the right side of the heart. This is where blood flows back from the entire body in through the atria. So blood comes back in through the right atrium up here, and if we open that window, just try and get a view there. So you can just see the outside there. Okay, so blood flows in. It's going to come in through here, and it's going to pass through a valve. Now we might get a better view of the valve up here. Okay, not particularly. We get a nice view when we open the whole chamber. That blood flows in here, and then it needs to pump to the lungs. So it goes in through one valve, and then the ventricle down here, this muscular part, is going to pump that blood this way. Okay, now this is a bit gross, but it's going to go out through here. Okay, there you go. So that vessel connects to the lungs. So your blood passes in through that valve, takes a detour, and is going to flow out towards the lungs that way. Okay, this is the pulmonary artery here. Okay, now I'm going to open this up a bit more so you can see the valves a bit better. So yeah, this is a garage dissection, so it's not going to be the cleanest dissection you're going to see. Now there's a really nice example of one of the valve leaflets. So let me get my little... So this structure here, that's one of the valve leaflets. And you can see all little cords attaching it to the cardiac wall there. Well, they're very important because they prevent the valve from turning inside out. So blood will flow in to the right ventricle from the right atrium. When that right ventricle contracts, it closes this valve, which is called the tricuspid valve. So these leaflets all close together, and it closes under high pressure. And without these tetherings to the wall, that's going to turn inside out. Okay, so that closes, but the pulmonary valve opens and allows the blood to pass to the lungs. Okay, and we might just get a view of the pulmonary valve. Okay, so just at this point where the tissue changes from cardiac muscle to blood vessel and turns white, you can see leaflets of the pulmonary valve. So there's one of them. They're very thin. Okay, we can talk about how they become diseased in a moment. Very, very thin. Okay, so those three will close together. There's three of those that close together to stop blood flow coming backwards. Okay, now I said blood travels to the lungs from there, and it's going to come back into the left side of the heart. Now the left side of the heart is really muscular. Okay, look at this kind of puny little right ventricular wall over this side, and when we open the left ventricle, we'll just see how much more muscular it is. So it's much thicker. So if we just cut that there. Now, that area there, that's the muscular wall of the left ventricle, left side of the heart. That's a comparison that side. That's the right ventricle. There's a little blood clot on my fingertip here. That's completely normal inside the hearts you're going to get from a butcher. But that left side of the heart is much thicker, much stronger. And if you think about all the boys and girls who go to the gym, okay, to build up muscle and muscle mass, and they're generally much stronger than somebody like me, it's the same for the left side of the heart versus the right side. This is much stronger, and it's much stronger because it has to pump blood to the entire body. This side pumps it to the lungs, which are essentially right beside the heart. Okay, now last thing I'll just do is open up this side. Okay, so there is a beautiful view of the mitral valve and its cords. Okay, so what we're looking at is this structure here. Okay, and you can see how it's tethered to the wall of the heart, the left ventricle, at these little tiny muscles, papillary muscles. And there's another one just behind it. Okay, so that's the mitral valve. That's actually my favorite valve, okay, because it's what I did my fourth year project on in university. That opens when blood flows back from the lungs. It opens to let blood into that massive left ventricle. When the left ventricle contracts, that valve is going to close and the blood is sent off. Just get a view there. It's sent up through here, okay, behind the mitral valve and out through the aorta. Okay, and that aorta, that's the largest blood vessel in the body. That's going to flow or carry oxygenated blood to the entire body. Okay, and essentially that's your garage dissection of the heart. So the heart itself, if you get hearts fresh from an animal, they can potentially be still beating, okay, when they come out. That's because they have their own pacemaker tissue inside the heart. Okay, and I suppose a topic of interest would have been the cardiac arrest suffered last week by Christian Eriksen in the football match between Denmark and Finland. And there's lots of different reasons for sudden cardiac arrest. Many of them relate to fibrillation, okay, which is where there's a disturbance in the rhythm of the heart. So normally we have a normal sinus rhythm that allows the heart to contract nicely and smoothly, generally, 70 beats per minute type of thing. With a fibrillation, there's a disturbance in the activity of the heart, and it becomes very chaotic, I suppose is the best way to describe it. So with sudden cardiac arrest, it could be that the heart stops. It's generally not. It's generally associated with reduced outflow from the heart, and that could be from a fibrillation, which is where the ventricle essentially just quivers like this, and vibrates. So it's not pumping blood out of the heart as it should. Okay. I should actually, since we have it here, have we much time left? We have this giant beef heart here, which I almost forgot about. So I'm just going to lift it over here. So I should say, before we look at that, the normal heart, the normal adult heart at least, is about the size of a clenched fist. Okay, so this lamb heart it's a bit smaller. Okay, the adult human heart is about the size of a pig heart, but this monster here, as you can imagine, it's from a cow, so it's going to be much bigger. Now, what I just wanted to show you is we have a view of the chambers here. Doesn't look too bad actually. Okay, so we have 4 chambers in the heart, or 2 inputs and 2 outputs really. So this one over here, and I just see a timer here where the camera's going to flick off in 20 seconds. But this chamber here, there we go. This chamber here at my fingertip, this is the right atrium, so this is the one where blood comes back from the entire body. What we see over here is the pulmonary trunk. So this structure is what carries blood to the lungs. Then we have the left atrium and ventricle on this side, and here we have the aorta. So we can pass a couple of, let's use cable ties. We were going to use a tap with water. So if something passes into the right atrium, the only place it can go is out through here. Okay, so blood goes in to the right atrium, down into the right ventricle, and it's going to pump blood out through this structure, okay, which is the pulmonary trunk. That's one pump of the heart. The other one is around the other side, and yes, this would have been much cooler with water. So here's the left atrium, so blood comes back from the lungs into here. The only place that can go is out that way, okay, through the aorta. So that's going to flow from here out through the biggest blood vessel in the body, the biggest artery in the body, out to all your bodies and tissues, and the whole cycle just continues and keeps repeating itself. Okay, so try it at home. Look back at the recording. Get yourself some pliers, a steak knife, a little choppy thing here, some punches, and yeah, do your own DIY dissection. Okay, so that's it for me, and don't know what's happening next, but Mark is going to sort it out.
Okay, thanks Tom. Now for something completely different. So one of the things that we're really interested in this lab is how do brains work? And the problem is that human brains are pretty complicated. So it's really difficult to start there. So we've taken an approach of looking at the simplest brains that we can find, the simplest nervous systems that really exist in nature. And that's probably the sort of nervous system that you find in an animal like the comb jellies that we work with, these little jellyfish-like creatures that we're going to show you a little bit more of later. We want to understand what their brains do, and what brains do is it produces behavior. Your brain controls what you do with your body, your behavior, how you interact with the world. The thing is that the world for these animals is the sea. So if we want to understand what their brains do, we want to understand their behavior, we need to go and look at them where they are, which is in the sea. So one of the unusual things that we do in this lab is we don't just work in this lab. We also sometimes go out into the sea and look at these animals to see what they're doing. So how do we do that? Well, to do that, we have these. This is a small remotely operated vehicle, or ROV, essentially an underwater drone. So this is one of the ones which we use, and this is called a Trident ROV. And it's a really nice piece of equipment, and you just connect a tether to it and it should power itself on. And there we go, nice flashing lights. And essentially what this has is a camera in the front, which you can see there, and it has 3 thrusters. So it has 2 thrusters at the back, you can see those propellers there, and it has 1 down the middle. And this gives it quite good maneuverability in the water. So we can drop this in, it's connected by this tether up to the ground, and we can get a feed from the camera. So we can maneuver it in the water and we can see what the camera sees and record it. Now, it's got 3 thrusters, which makes it fast and maneuverable. You can see it's got this nice sort of hydrodynamic shape. It gets through the water quite easily. But the way this is set up is pretty limited. So it can go left and right in the water, it can go forwards and backwards, and it can pitch upwards and downwards. So it feels very much like flying an airplane, as it were. It's a lovely piece of kit, but it's, you know, a sealed black box. And the biggest problem with this is that the company that makes it don't make it anymore. So we have another one which is a little bit more interesting for reasons I'll explain in a moment. Okay, so this is our other ROV. And this is a much more interesting piece of kit. It's a bit bigger, it's a bit chunkier, as you can see, but it's also cooler for a couple of other reasons. So this is made by the kit, the basic components of it, are produced by a company called Blue Robotics, but what they send you is a box of parts. So we had to actually put this thing together ourselves. And that comes with a lot of advantages. The first thing you'll notice, obviously it's bigger, but we've got 2 thrusters front and back here. We've got 2 thrusters front and back here. And then if we look on the top, we've got 2 more thrusters. And that gives this much greater freedom of movement. So in the water, this can go forward, backwards. It can go straight up and down. It's quite heavy. You can also rotate, you can move sideways. And at the front you'll see this little dome there, and in that dome is the camera, just like on the other one, but this camera can pitch up and down. It's on a little gimbal, so this can actually tilt up and down. So you can go forward in the water, but pitch the camera down and watch beneath you. So it's got much more control. But that's not why it's most interesting. Why it's most interesting is because of this modular... Right. Okay, so here it is. We'll just open the battery compartment at the back, so let's just connect the battery. That's very loud. I'll give you a little look around. Okay, so I'm going to give you a little guided tour here. So at the back here is where the tether comes in, and we have all of these connectors which connect out to the motors and so on. And as you can see here, because you got this clear plastic tube, you get a really clear look at what's going on inside. So here we've got the speed controllers for each of the motors. And here we've got this with the flashing lights at the top is a Pixhawk system, which is actually an autopilot system. And then controlling the entire thing, we've got this Raspberry Pi. So as you can see, it's actually a very simple piece of equipment. So this looks like a complicated piece of equipment, but as you can see, if you look at the actual components, there's nothing terribly unusual there. It uses fairly basic, standard, off-the-shelf components. The sort of things that a lot of people who play around with radio control vehicles and things like that might get their hands on. So we got speed controllers here to control the thrusters, and these are exactly the same sort of thing as you might have on a quadcopter, on an aerial drone. We have an autopilot system, a Pixhawk system, which is actually designed for an aerial drone. Exactly the same device. What does that allow it to do? Well, it allows it to control all of the motors together to allow it to move forwards, backwards, left, right, up and down. Exactly the same as an aerial drone. It also allows the vehicle to hold its position in the water. So if it starts to tilt over, it will straighten itself up. Exactly like an aerial drone. So piloting this is exactly like piloting an aerial drone, except instead of going through the sky, you're going through the water. And it's pretty user-friendly. But the real advantage of a system like this is that it's customizable. So we put this together, like I said, it arrives as a kit, but it's completely open source. So the hardware and the software is completely open, completely customizable. You can add whatever you want to it. You can add more sensors, you can add sonar, you could add robotic arms, anything you want. And actually, this is the basic configuration that we have here. The one that you're looking at now, we just have this set up with camera and autopilot and so on. But what we're working on next is adding a light sheet system. So just like the light sheets that we showed you earlier, we're planning on actually adding light sheet generators and imagers, which will allow us to actually see the ocean in 3 dimensions and see what's in there. So maybe next year we'll be able to show you some of what we've been up to with that. So this is the equipment that we use, but there's no point in me showing you this unless I show you what we can do with it. So we were out earlier this week in Wicklow Harbour and we had these things in the water. Let's see some of the footage that we caught.
So here we are down in Wicklow Harbour. We've got our ROV with us and we're about to put it into the water and see what we can see.
Here we go. Okay, folks, this is our last segment that we're going to do today. There's so much light on me here. I feel like I'm going to spontaneously break into a makeup tutorial, but hopefully not. The light's there for a reason, which I'll explain in a second. Oh yeah, and you know we're professionals because look, costume change during the interval. It's just like the Eurovision. Right. So far we've kind of shown you a couple of ways that we have, and hopefully you've learned something about, how to explore the world around you and really sort of get out and discover things. Observation is really important, but one of the things that we do as researchers is observation is actually mostly a huge part of what we do. But when you observe things, when you observe the world around you, you develop questions. And then to answer those questions, you come up with an experiment. So what we're going to do now is we're going to do an experiment. Now, this isn't a demonstration, right? This is not something where we know what's going to happen. When you do an experiment, you don't know the answer. That's kind of the point. And this is an experiment we have never done before. So I genuinely don't know what's about to happen. Don't get too excited. It might not be that interesting. But let me explain what we're going to do. Right down here, below me here, is a little light box, and sitting on top of that, we've got a little dish with one of our comb jellies in it. I'm going to switch to that now. Now, unfortunately, the light's a little bit flickery, so it's going to be kind of annoying, but it's the best I can do. Let me just transition to that now. Okay, so you should be able to see there's a round dish that we have, and you should just be able to make out one of our little comb jellies. So I'm just going to give him a little bit of a poke there just to get him moving around. And there you can see him there. So they're almost completely transparent. So it's going to be very difficult to actually see them properly, but hopefully you can see there. And you can see, what you should be able to see is as he's swimming around in the dish there, he's got his tentacles out. So those tentacles are covered in adhesive. So the adhesive that these guys use, we don't really know exactly what it is or what it's made of, but it's one of the areas that we research actually, is trying to understand what this adhesive is, and potentially is it something that we can harness, and is there something useful we can do with it? Because this is an adhesive that seems to work very quickly and seems to work underwater, obviously. And there's lots of potential uses for a fast-acting adhesive that works in a wet environment. Whether that's from sticking something onto the underside of a boat, or the other wet environment that's interesting is the human body. So potentially you could use this for something like wound closure, or drug delivery, or all of these sorts of things. So this is one of the reasons why we're interested in these little fellas. Now, why do they have these sticky tentacles? Well, that's how they catch their prey. So we want to understand how it is that this adhesive is released, because the adhesive doesn't sit on the surface of the tentacles. It's held on the surface of the tentacles are cells which actually contain the adhesive packed inside. And when it comes into contact with food, it bursts open and releases the adhesive. So we don't know what causes it. So maybe it's different materials. Maybe it responds differently to different materials. And that's what we're going to do now. So I'm going to just cut back to our view, and I'm going to show you a slightly different chamber. Now, let me just arrange this so that you can possibly see what we're doing. So, there. So this is the same type of dish that you just saw. In this case, though, we've got this little boundary, this green layer around the edges. And you'll also see these little pillars sticking up. And on this side, 1, 2, 3, they're made of metal. So these are actually just little prongs of wire. So if I was to stick my finger into it, it would be quite sharp and pointy, but at the scale of a ctenophore, this is like, at the scale of our comb jellies, this is basically like a big pillar in the water around them. And on the other side, we have 3 pillars made of plastic. And specifically, it's PLA, it's polylactic acid, which is the same stuff that we 3D print with all the time. So we've got a plastic, and we also have a metal. And we want to know, is there a difference between how their tentacles respond? So if they trigger their adhesive, then when their tentacles come into contact with the pillars, they should stick. And if they don't, it should just brush past them. and we have no idea what the answer is going to be. So what we're going to do is we're going to get this little fella and we're going to pop him in to that dish. And I'm going to try to do it without spilling everything everywhere. And there he goes. So he'll probably pull his tentacles in at first. And you can see he's just swimming around trying to see where he is. So we don't know where he's going to go. So one of the things you have to do when you do an experiment like this is you have to, you know, if it only sticks to the plastic, you need to think about, well, does he ever go anywhere near the metal? So you have to think about what do you measure. There's lots of different things you can measure. But right now, we just want to observe and see what happens. And right now, he doesn't seem that interested. There's a really good chance that nothing interesting is going to happen here. This is one of the things about doing research. A lot of the times, sometimes you make big discoveries, you get surprises. And sometimes nothing much happens at all. This could be the latter. So I'm just priming you for that. Be ready to be disappointed. Now, let me see if I can just shove him around a little bit. So unfortunately, and he's bumping into things. Unfortunately, he's sucked his tentacles all the way back in. So let's just carry on there for a minute and see does anything at all happen. We need to get his tentacles out. We can't force them out. What you may be able to see there, if I zoom in a little, let's see, can I zoom in a bit tighter? No, that's about as tight as I can go. You might be able to see there's little tiny specks on the surface, little particles floating on the surface. And the only current that's in that water is what he's generating. He or she, I don't know why I'm saying he. They're hermaphrodites, they're both male and female. So you can probably see a little shimmer on the surface of the body and down these little rows, these little 8 rows, and these are the comb rows. That's why they're called comb jellies. And this is what they use to kind of make their way through the water. And right now it appears to be trying to swim downwards. And it's creating little vortices and little currents within the water. And you can see the little particles floating on the surface, just sort of floating around as a result of that. I'm going to try to take out some of the water. There might be a little bit too much water in there. Problem solving in real time. Now, let's see if I can convince him to do anything other than swim downwards. This might be the worst experimental demonstration I've ever done. We're just sitting here looking at nothing happening. Oh, he's turning around and trying to swim downwards again. Right. Maybe we'll try another one. Just a second. So if they do get stuck, it's not a huge problem to them. Oh, there we got tentacles out. It's just skirting the edge of that metal one, so we haven't made contact yet. At least one of them's behaving. Oh, it's pulling in his tentacle. If it does get stuck, then what will probably happen is the tentacle will break off. And this is normal. This is what happens to them all the time. Their tentacles are very, very fragile, so they tend to snap away and then they'll just grow back again. So as far as we know, it's not a huge problem for them. Now, unlike the first guy who really wanted to swim downwards, this guy really seems to want to swim upwards. Let me see. I can just focus that a little bit better. There we go. So we got a tentacle out there. It's so close to the metal, but not close enough. Nope. He's teasing us. Oh. Ah. Ah, now, look at that. That looks like it's stuck, doesn't it? So their tentacles are very, very long when they stretch them out to full length. Oh, it's pulled it away. It hasn't stuck. So the first time we contacted the metal there, it hasn't quite stuck. But I think he stuck himself on the plastic. I think he's wedged himself in there. I might need to shove a little bit. And, oh, there's a tentacle out. No. Alright, we'll see if we can get, it's going for the same one again. Is it? No, it is not sticking. It is not sticking to the metal. It's ended up back in exactly the same place as the last time, though. Let's see if we can help it through. There you go. Oh. Is that stuck to the plastic or not? That tentacle has definitely come into contact with the plastic. But I can't tell if it's stuck. Nope. Oh. So, it doesn't seem to stick to either. Right. We might leave that go for another little bit, but I won't bore you with it any longer. Oh, we got two tentacles there. Let's see. We got one more contact. Let's see. Come on. We need to design a better arena for them, I think. No. Looks like it's touching against the metal there again, but not triggering it. Okay, we will leave it there. Right, so I warned you, it might be nothing. Sometimes that's the answer. But why might this be interesting? Well, one of the reasons why we might be interested in looking at how plastic interacts with them is because of increasing concern. People are worried about environmental microplastics, in particular in the ocean. And we don't know how it affects these types of animals. So because they just drift their tentacles out in the water, potentially, if they drift into a piece of plastic, they might try and eat it. But only if the plastic actually activates their tentacles, activates the adhesive to be released. And from what we've seen there, it doesn't look like just a brief contact with the plastic is enough to do that. So we can't say, and this is just one experiment, we only watched for a few minutes. To answer this properly, we need to do this over and over again. We need to think very carefully about our experimental design, but at least in the first glance, there's no obvious sign that either plastic or metal has a significant effect on causing their adhesive to be released. But there we are. That's what scientists do all day. Well, that's what we do all day anyway. Right, I think that is it. I think we are pretty much finished. So, thank you very much, everybody who joined us, and hopefully next year you will see us again. Hopefully we'll be in a field and not online. If anyone has any questions, you can drop it into the chat. We'll be around in Gathertown for a little bit, or if you're watching this back later, feel free to drop us an email. Thanks very much, folks. Bye.